Hello, welcome to this lecture on computer power system analysis. In the last lecture, we have discussed about the unknown quantities as well as the equations corresponding to this AC/DC load flow. And we have seen that in the case of HVDC system, there are actually 5 equations which do describe the operation of an HVDC link, but then there are 9 unknown quantities involving both the rectifier side as well as the inverter side. Now, we have argued that because there are only 5 equations, but 9 unknown quantities, so then therefore we need to pre-specify 4 quantities and then subsequently we can solve the remaining 5 quantities utilizing this 5 equations. Now, here the question comes that out of these 9 quantities, which 4 quantities we actually need to pre-specify and then which 5 quantities we actually need to solve. Actually, as it happens that out of these 9 quantities, we can basically pre-specify any 4 quantities and it is possible to calculate the remaining 5 quantities utilizing these 5 equations. So, now let us look at some example. So, in this example, so case 1, so let us say some case we will be actually discussing 2 cases. So, in case 1, let us say the specified are specified quantities these specified quantities are alpha PDR, gamma VDI. Now, you may wonder that we are actually trying to calculate PDR, but then here we are actually specifying PDR. Now, the answer lies the fact that whenever we are actually specifying an HVDC link, we usually say that this HVDC link is at this particular moment is let us say supplying 1000 megawatt, because whenever we are trying to solve the load flow solution of any AC/DC system, so in that load flow solution we need to know that what is the amount of power which is being carried by the HVDC link. Until and unless we do not know that what is the power being carried by the HVDC link, we really cannot solve for this AC and DC system together. So, then therefore, because we already know that what is the amount of power being carried by this HVDC link, so it is quite a practical assumption to know that this value of PDR is actually available to us. So, we have got this 4 quantities known. So, then utilizing these 4 quantities, we now need to calculate the remaining quantities. That is, our final goal is to calculate all the other quantities in that particular vector, unknown vector, that is basically all the remaining 6 quantities, plus we also need to calculate QDR, PDI, QDI and 6 other quantities, So, this is our goal. So, we need to solve from these 4 quantities and these 5 equations, we need to solve all these other quantities. So, let us see how to do this. So, we will solve it in steps, and these are very simple steps, nothing. So, steps. So, first step, PDR is known. Now, PDR we know that PDR is actually VDR into ID. Now, what is ID? ID is actually VDR into VDR minus VDI by RDC. Please note that this RDC is also known. RDC is nothing but the resistance of the HVDC link, and here we assume that all the parameters of all the lines, that is all the AC lines as well as the HVDC link are known. So, then therefore, RDC is known. So, then therefore, from this, so then we can write down this equation as PDR into RDC is equal to VDR square minus VDR into VDI. So, we can write down as VDR square minus VDR VDI minus PDR into RDC is equal to 0. So, this is a quadratic equation involving VDR. Now, in this, please note that this VDI is known, it is already pre-specified. So, this VDI is known, PDR is already known because it is already pre-specified, RDC is nothing but the HVDC link, RDC is nothing but the resistance of the HVDC link, which is also known. So, then in this quadratic equation only unknown is which is VDR. So, now because everything else is known, so then we can calculate VDR. So, VDR can be calculated. Now, here there is one little question. The little question is that it is an quadratic equation. So, then therefore, we will get two values of VDR. Which value of VDR we should take? We should only accept that value of VDR which is greater than VDI, because after all the current can only flow from rectifier side to inverter side, but it cannot flow from inverter side to the rectifier side. So, then therefore, out of these two values of VDR we should only choose the value which is greater than VDI. So, we choose the value which is greater than VDI. Then step 2, once we know VDR, then we calculate ID, we calculate ID is equal to VDR minus VDI by RDC. So, here VDR we have just now calculated in step 1, VDI is already known, RDC is known. So, ID is calculated. Now, what we do? So, now we go to step 3. In step 3 we write that VDOR is equal to VDR plus 3 by pi XCR NR ID divided by cos alpha. Now, from where we have got this equation? We have got this equation from please recollect that there is one equation that VDR is equal to VDOR cos alpha minus 3 by pi XCR NR into ID. So, then therefore, if we just rewrite this equation, we get this expression of VDOR. Now, in this expression what happens? Now, in this expression what are the quantities known? Alpha is known. So, alpha is known, ID we have just now calculated in the last step, VDR we have calculated in the first step, XCR and NR they are all known quantities. For example, you have already said in the last lecture that for a 12 pulse HVDC link NR is equal to 2 and XCR is nothing but the transformer leakage and XCR is nothing but the transformer leakage reactance. So, then therefore, in this expression everything is known. So, then therefore, VDOR is known. So, therefore, VDOR is known or calculated. Right. So, VDOR is calculated. In step 4, what we know, what we calculate? We have already seen that we have got an equation which says that VDR is equal to VDOR cos phi r. We have already seen this equation in the last lecture, and so then therefore, cos phi r is VDR by VDOR. Now, in this VDR is known, VDR we have already calculated in the first step, VDOR we have just now calculated in the last step. So, then therefore, cos phi r is known. So, then this is the third quantity we have calculated. So, now here you see there are 6 other quantities. So, then this is one quantity we have calculated, this is another quantity we have calculated, this is the third quantity we have calculated, right. So, out of the 6 quantities we have already calculated 3 quantities. Now, once we know cos phi r, so then we can calculate q dr is equal to p dr tan phi r. Phi r we have just now calculated, q dr and this p dr is already pre-specified. So, then therefore, I can calculate q dr. So, then it is calculated. So, it is calculated. So, here also q dr is calculated. Now, in step 6, we write that V dor is equal to, V dor is equal to 3 by 2 by 3 root 2 by pi n r a r e t r. Now, here in this expression, V dor we have just now calculated, V dor we have just now calculated in step 3, nr is known. Now, if we know ETR, we would be able to calculate AR. Now, from where ETR will come? Now, please again recollect our discussion regarding the basic procedure of the sequential AC/DC load flow. What we do in the case of sequential AC/DC load flow? We first assume the flat start. Please note that essentially it is an AC grid, and in this AC grid between two buses we have got one HVDC link connected and we are trying to solve for everything. So, then when we start our sequential load flow, what we do? We first take the flat start. So, then therefore, the moment we do take the flat start, so then therefore, this value of ETR is already known. Initially at this value of ETR is known. So, then therefore, initially when we are starting our calculation, this ETR is known. So, once this ETR is known, so then therefore, AR is also known. So, then I should actually, so therefore, AR is calculated. So, out of the 6 quantities, so this is the 4th quantities we are calculating. The rest 2 are, so then we have still have to calculate 4 more quantities. Which 4 more quantities? 2 quantities from here and this PDI and QDI. Step 7, we calculate PDI as VDI into ID. Now, in our specification VDI is already known. So, then therefore, so PDI is calculated, right. So, PDI is calculated. So, we, because VDI is known and PDI is calculated. So, PDI is calculated. So, here this PDI is also calculated. Then what do we do? Then we again write down the equation VDOI is equal to VDI plus 3 by pi XCI N I I D by cos gamma. Now, here in this equation VDI is already pre-specified, gamma is pre-specified, ID we have calculated, Ni is known, Ni is number of 6 pulse converters connected in series at the inverter side, Ni is known, and XCI is nothing but the transformer leakage reactance at the inverter side. So then therefore VDOI is also calculated. So then therefore VDOI is calculated. So once we know the VDOI, so then after that what we do is we calculate cos phi I is equal to VDI by VDOI. So then therefore cos phi I is calculated. So this is the fifth quantity we are calculating. Right? This is the fifth quantity we are calculating, because here VDI is known. This is actually pre-specified, and VDOI we have just now calculated. Once we know cos phi I, so then in the next step I can calculate QDI is equal to PDI tan phi. So then therefore QDI is calculated. So in this QDI is also calculated, and out of the 6 quantities we have already calculated 5 quantities. Which one is remaining? Remaining is AI, that is the transformer tap ratio at the inverter side. So to calculate the transformer tap ratio, what we do is we write that VDOI is equal to, 3 root 2 by pi Ni AI ETI. So here VDOI you have just now calculated from step 8. Ni, which is known, Ni is nothing but the number of 6 pulse converters in series at the inverter side. ETI, again when we start our iteration, we first take this a flat start. So then therefore ETI magnitude is also known. So then therefore when ETI is known, everything else is known. So then AI is calculated. So AI is calculated. So this is the 6th quantity we are solved. So then therefore by following this very simple algebraic steps, we are being able to calculate all the 6 remaining quantities as well as the quantities which are of our interest. So now what happens after we finish this calculation? So then therefore after we finish this calculation, after finishing this calculation, so therefore PDR, QDR, PDI, QDI are known. Once they are known, so then after that what we do? So utilizing these equivalent injections, we now solve one iteration of the AC load flow, just one iteration. We do not solve this AC load flow completely, we just do the one iteration of this AC load flow. After we do this one iteration of this AC load flow, so then what we get? So then we write, so utilizing this, values, we carry out one iteration of AC load flow, and thus, and once we carry out one iteration of AC load flow, so then what we get after we carry out the one iteration of AC load flow? We get the updated values of ETR and ETI, and therefore updated values of ETR and ETI are obtained. So, once we get this updated value of ETR in ETI, so after that we again recalculate, we again follow steps 1 to 11. So, after we get this updated value of ETR ETI, so then therefore, we again follow the steps to 1 to 11, update the values of PDR, QDR, PDI, QDI, do another iteration of AC load flow, then we get another updated values of ETR and ETI, then again simply follow the steps 1 to 11, then get updated values of PDR, QDR, PDI, QDI, then again solve another iteration, get updated value ETR, ETI, and then come back. So, we keep on doing this iteration till this AC load flow converges in the usual sense. So, that is how this particular algorithm actually works. So, we can see here that although these equations are completely non-linear, because out of these 5 equations, 4 equations involve cosine terms. So, then therefore, 4 equations are completely non-linear, but then we really do not have to invoke any kind of complicated Newton-Raphson technique or etc. For solving these 5 equations, we can simply solve for the remaining unknown quantities which are left after our pre-specified quantities. We can simply solve these remaining unknown quantities by simple algebraic manipulation of these 5 equations. So, then therefore, these calculations are really very computationally light, and because they are computationally light, so then therefore, the overall efficiency of the AC/DC load flow is not really hampered much, not at all hampered much. It is very little enhancement of this code. So, this is the basic philosophy. Now, we have just now only seen only one case when we have got specified quantities alpha, PDR, gamma and VDI. Let us take another case and then let us see that how these calculations. Now, here let us say that instead of PDR and VDI, we just let us say reverse them, we just see that VDR and PDI is known and alpha and gamma. So, then in case 2, so now let us consider case 2. So, in case 2, just it is another example, in case 2 alpha, gamma, PDI and VDR are specified. So, if alpha, gamma, PDI and VDR are specified, so in the earlier case we said that alpha, gamma, PDR and VDI, now here we are seeing alpha, gamma, PDI and VDR. So, then how do we calculate this? So, the steps are very simple. This goes in a very this almost on the same manner. So, we say that PDI, we know that PDI is equal to VDI into ID. So, this is nothing but VDI into VDR minus VDI into RDC. So, we can write down that RDC PDI is equal to VDI VDR minus VDI square. So, then therefore, it is VDI square minus VDI VDR plus RDC into PDI is equal to 0. Again, this is a quadratic equation involving VDI. In this quadratic equation, which quantities are known? The quantities known are VDR, which is specified, PDI, which is specified, RDC, which is known. So, then therefore, this is a quadratic equation. We can solve for this quadratic equation by the standard technique. We get two values of VDI. we take that value of VDI which is less than VDR. So, we here in this case we have to take that value of VDI which is less than VDR. So, once we get this value of VDI, so then what we do is then we calculate ID is equal to VDR minus VDI by RDC. So, then from here we write that VDI is calculated, then here also ID is calculated. Once we know ID and VDI, after that what we do is, if we just look at it, after that we can simply follow this step 3, step 4, step 5, step 6, step 7 up to step 11 as it is. Then we can calculate all these other quantities. So, now what are the major steps? So, then basic algorithm of this AC/DC load flow. So, then how do we simply write down the basic algorithm for? So, let us just a schematic algorithm, schematic, rather I should say overall algorithm for AC DC load flow. So, what are the overall algorithms? So, overall algorithm is that first we take, assume flat start, for the AC system. So, we assume flat start for the AC system. So, then therefore, ETR and ETI is known. Then we write that solve the DC equations to calculate PDR, QDR, PDI, QDI. Then what we do? We run, or rather run or execute one iteration of AC load flow. So, when we run one iteration of AC load flow, then we get the updated values of ETR and ETI, and then again we solve the DC quantity, etc., etc. So, then therefore, what we say in the next, that go to step 2 till convergence is achieved. So, this is a very basic algorithm for AC/DC load flow. So, that is how. So, we can see that there is no change in the AC load flow and etc. So, we have already explained all these things. So, now let us look at some very simple example. So, in this example, again we take this 5 bus system. So, one bipolar HVDC link is, now what are we now saying, that in this 5 bus system we have got one bipolar HVDC link is connected between bus 4 and bus 5, rectifier at bus 4 and inverter at bus 5. The basically the base voltage of the AC system is 132 kV. One thing we must actually mention here, that the calculations at the DC side we usually do in the actual values. Calculations at the DC side we actually do in the actual values. So now, these are the various quantities. Rd is nothing but the DC link resistance. Nr is equal to Ni is equal to 2 because we are considering 12 pulse converter LCC, and XCR it is actually given 3 by pi into this. I mean, we are taking XCR and XR, it should be XR and XI, which is nothing but basically transformer leakage reactance at the rectifier, transformer leakage reactance at the inverter. This is equal to 6, that is 3 by pi, this is 6. Now, the first combination, what I have said, that in the combination alpha we have assumed 5 degree, PDR 100 megawatt, alpha 18 degree, gamma 18 degree, the extinction angle, VDI this. Now, because everything is given in megawatt and MVR and etc., so we calculate everything in actual values. I mean, we do not do the calculation in the DC side in the per unit values, we do the calculation at the DC side in the actual values. So, when we do these calculations in the actual value by following these steps, we get VDR is equal to this value, ID is equal to this, QDR is this, PDI, QDI, everything. So, all these values are known. Once we know these values, so now we calculate the equivalent injection at P4. Now, please note, in the 5 bus system, originally at 5 bus system there was already a load connected 115 megawatts. So, in per unit it is already minus 1.15. On top of that, PDR is 100 megawatts, so that is equal to minus 1. So, then therefore, now the net power injected is this plus this, that is minus. So, now net load at bus 4 is actually 215 megawatt. So, that translates into 2.15 per unit. At bus 4, the basically the reactive load which was already connected was 60 MVAR. So, this is minus 0.6, and here we have got, and also this is absorbing 16.276 MVAR. So, in per unit is 0.16276. So, then therefore, net reactive power load here is minus 0.6 into point this plus this. So, it is, so net reactive power load at bus 4 has also increased. So, it is minus 0.7626. So, this plus this. At the inverter side, at bus 5, the original AC load connected was 85 megawatt. So, then therefore, it has, so basically corresponding to that load, my injected real power is minus 0.85. But the inverter is injecting a value of PDI, it is giving into this AC bus a value of 98.45 megawatt. So, then therefore, net injected power would be equal to this minus, because this is load, plus this is the generation as far as bus 5 is concerned, this is generation. So, then net real power injected is this plus this, so 0.1345 per unit. And at the rectifier side, and at the inverter side, QDI is 35.024 MVAR. Please note that both inverter and rectifier, they do absorb reactive power from the AC grid. So, then therefore, as far as this AC grid is concerned, this inverter is also acting as a load, as basically is also acting as a reactive power load. So, then therefore, this is the reactive power load due to this QDI, and this is the earlier AC reactive power load which was connected, which is actually 40 MVAR, which is already connected. So, the net reactive power load at bus 5 is increased. So, then these are the new quantities. So, then please note that in the DC side we are doing the calculations using the actual values, but when you are converting them into the AC side, we are converting them in the per unit values. And please note that this base MVA is same in everywhere, at the AC side and the DC side, base MVA same. So, then once we get these equivalent values of net values of P4, Q4, P5, Q5, we do run one iteration and then update the values of ETR and ETI, and then again recalculate and recollect, and then again keep on doing this. And once we do this, then then this whole algorithm converges in a total iteration of 5 iteration, and these are the results. And if you compare these results, you will find that these values have actually gone down significantly because of this fact that at bus 4 and bus 5 this rectifier and inverter converter, they are actually acting as reactive power load. So, as if there is an extra reactive power load. So, then therefore, their voltages has gone down, and the net P inch and etcetera, that also changed. In this case, net P inch has got now minus 0.25, and here it also increased, and this net Q inch etcetera have increased, and these are the final values of ER and AI. So, that is how this AC/DC load flow is executed. So, this is the end of our AC/DC load flow. So, from the next lecture onwards, we would be looking into the other aspects of this particular course. Thank you.